birational geometry. Shunsuke, you may begin your talk.
Okay, thank you very much. Then let me share the screen. So can you see two blank notes?
Yes, yes, yeah, 1 and 2.
Yeah. Oh, thank you. Then, yeah, in the last talk, I defined F regular and F pure rings, and also KLT and log canonical singularity. So first, let me explain the correspondence between these two. So F singularity and singularity in characteristic zero. And I use the technique reduction modulo P. So first, okay, let me start with this ring R. This is a quotient ring of polynomial ring over C by F1 dot FR. And let me take localization. And I assume this ring is Q-Gorenstein and normal. So this is a ring of characteristic zero. And take A. So A is a finitely generated G subalgebra of C. Maybe, yeah, A is a subring of C. And let me assume A is regular. And I take also R sub A. This is a subring of R. Again, this is finitely generated, and this is flat A subalgebra. As such that R sub A tensoring with C over A, this is isomorphic to R. So tensoring with C, we recover R. We can take such A and RA. Of course, so they are not unique, but we can always take such A and RA. And yeah, of course, easy remark is if polynomial Fi, the coefficient of the the coefficient of the Fi integer, then so if the coefficient if the coefficient of the Fi integer, then we can take A to be G and R sub A to be the quotient of polynomial ring over Z. So this is a kind of baby case. Okay, and when mu is a maximal ideal over A, so mu is an element of spec A, and I assume this is a closure point, which means maximal ideal. Then I denote by R mu. So this is a R sub A tensoring with A sub, R sub A tensoring with A over mu, and I take its localization. Then since A is finitely generated Z subalgebra, A over mu is a finite field. So R sub mu is a positive characteristic. R sub mu is a ring of positive characteristic. Again, if the quotient, so maybe if we can take A to be Z and R sub A is a quotient ring of a polynomial ring over Z, so which means the case the quotient of the Fi are all integers. In that case, so if A is equal to Z and R sub A is the quotient of polynomial ring over Z, in that case, so prime P is a maximal ideal of A, now A is a Z, and R sub P is nothing but localization of the quotient of polynomial ring over Fp, so like this. I take its localization. Okay. Then the following is today's one main result, theorem 1. So this is a combination of result of Watanabe. So Watanabe, Meta Srinivas, Hara, Mashwid, and Sato and myself fix A and RA as above. Then following three conditions are equivalent to each other. The following three conditions are equivalent to each other. First condition is the ring R. R is a ring of characteristic 0. This is KLT. The second condition is, so there exists a non-empty open, so this is open subset of spec A such that R mu is F regular, maybe Q Gorenstein and F regular, Q Gorenstein F regular for all mu in U, and mu is a closed point, which means the maximal ideal. And third condition is there exists one mu in spec A. There is one maximal ideal, maybe closed point, such that R mu is Q Gorenstein F regular. So okay, so this is a statement of theorem 1, and yeah. So let me explain the baby case, which means that if A is equal to Z and R sub A is equal to the quotient of polynomial ring over Z, in that case, second condition is equivalent to saying that RP RP is this RP. RP is Kilgorenstein F regular for all but finitely many primes. Yeah, so basically almost all P, for almost all primes, RP is F regular. And the third condition is equivalent to saying that RP is Kilgorenstein F regular for 1P, for some P. And yeah, I cannot explain the proof of this theorem, but let me explain the history about this theorem. So first, 2 implies 3. This is clear. This is trivial. And 2 implies 1. So this part was proved by Watanabe. Maybe 1990s. And first condition implies second condition. This part was proved by Meta, Srinivas, 97, and independently by Nobuohara, 1908. Yeah, these part are so in some sense a classical result, and but 3 implies 1. This part, Marsh-Schweid proved the case. R sub A is Kilgorenstein, and dimension of A is equal to 1. Yeah, they are assuming A is a dedicated domain, but now Sato and myself proved the general case. So we don't we can allow any regular link as A, and we don't put a Kilgorenstein condition on RA. Put general case. Yeah, we are assuming R and RP Kilgorenstein, but it does not. So it does not imply RA is Kilgorenstein. RA is Kilgorenstein's stronger condition.
Excuse me.
Yes.
2 to 1 is joint work with Hara. So
yeah, but maybe in a no boundary case, so you proved in a very early stage in the yeah. Okay. Yeah. Sorry, I should write. Okay. Yeah. Okay. Yeah. Sorry, I should write hello. Sorry, I should have written Hara Watanabe, and then published year is maybe 2004. Yeah, I guess. Sorry.
Thank you.
Sorry. Yeah. Okay. So then basically, so you can check. You can check R the KLT condition by looking at a single modular P reduction. That is a quite recent progress. And so this is cell 1 is about KLT singularity. And next, let me discuss log canonical singularity. And that is theorem 2. Again, this is a combination of results of sorry, then Hara Watanabe. And sorry, Fujino myself and Sato myself. Sorry, I should have mentioned. So Mashuid paper is quite recent. This is a yeah 2018 I think. And so Sato and myself, this result is just very recent result. And okay, then so let me discuss the log canonical case. Then log canonical case is a little bit more subtle. So consider again I fix A and RA and consider following three conditions. First one is R1 is log canonical. The second one is there exists U but now this is not open. This is just a dense subset such that R mu is Q-Reinstein FPR for any mu in U. The mu is a closed point. And third condition is there exists one mu. This is a closed point of spec A, so which means the maximal ideal. R mu is a Q-Reinstein FPR. Then, so for now, we know what we know is 2 implies 3. So of course this is trivial, and 3 implies 1. This holds. And if the ring is isolated singularity of dimension at most 3, in that case, 1 implies 2. Yeah, this is a statement of theorem 2. We believe these 3 conditions are all equivalent, but at the moment, yeah, we don't know how to prove 1 implies 2 in higher dimension case. And okay, yeah, let me give one remark. So if A is equal to G and R sub A is equal to the quotient of polynomial ring over G, in that case, second condition is equivalent to saying RP is Q-Gorenstein F pure for infinitely many P.
There's a question from Kaushik whether U is dense in maximal spectrum.
Oh yeah, yes. Sorry, sorry about that. Yeah, yes. Yeah, I should have written the. So it's a dense subset of closed points. I'm sorry. Yeah. Yeah. Thank you very much. So then, yeah, when A is equal to Z and R sub A is a quotient of a polynomial ring over Z, in that case, second condition is equivalent to saying that RP is Q-Gorenstein FP for infinitely many P. So this part is different from the KLT case. KLT case, yeah, here we look at for all but finitely many primes. So basically, for almost all P, all primes, so RP is F regular. But in the log canonical case, only maybe something wrong. Yeah. So yeah. Anyway, only infinitely many primes RP is Q-Gorenstein FP. Yeah, I will show you example. But before giving you an example, baby example, let me tell you a history about theorem 2. Again, so remark is again 2 implies 1. This part is in some sense classical. This is due to Hara and Watanabe. Uh, 2004. And 3 implies 1. So this is our new part, and this is due to Sato and myself, 2020. And 1 implies 2. I mean, the case, I mean, R is isolated and R is isolated singularity of dimension at most 3. In that case, so this case was proved by Fujino and myself at 2013. Yeah, and so implication 1 implies 2. This part is closely related to arithmetic problems, so which makes the problem difficult. Yeah. Anyway, so this is a history, and let me show you a baby example, which basically I already explained in the last talk. So let R be a quotient of three-dimensional polynomial ring by x cubed plus y cubed plus z cubed, and take localization. In that case, we can take A to be Z and R sub A to be a quotient of polynomial ring over Z. And this case, RP is a localization of FP algebra like this. Then, so as I mentioned in my previous talk, RP is F pair if and only if P is equivalent to 1 modulo 3. So this is due to Fedor's criterion. So our U is a prime, and P is congruent to 1 modulo 3. So this is, of course, dense subset, but it's not open. So in theorem 2, you cannot be open. So yeah, this is a difference between the KLT case and log canonical case. And okay, let me go back to KLT case. So KLT case here, and yeah, especially let me look at a case A is equal to Z. In that case, so if R is KLT, then RP is Q-Gorenstein for almost all P. But in this theorem, so we don't know how large P has to be. But in dimension 2, we know. So we know how large P has to be. So let me explain this. So this is a specialty of a two-dimensional case. Okay. Okay. This is theorem 3. Again, this is due to Hara and Sato and myself. Let R be a F finite. So two-dimensional F finite normal local ring of characteristic P if R is KLT and P is greater than 5, then R is F regular. So in dimension 2, whatever the ring is, so if characteristic greater than 5, then KLT condition implies F regularity. Yeah, this is quite useful result. And but so let me give a remark. So here, so I said KLT, but in my previous talk, I defined KLT singularity only in characteristic 0. But since resolution of singularity exists in dimension less than or equal to 3, in that case, resolution of singularity exists. So we can define KLT and log canonical singularity in dimension at most 3. And one more remark. Sorry. one more remark is, so Hara proved the case residue field is algebraically closed. But now I will discuss the application of theorem 3 to a geometric problem, and for that application, we cannot assume residue field is algebraic closed. Yeah, I will explain later. Yeah, before explaining a geometric application, yeah, let me give one more remark about theorem 3. Theorem 3 is just a specialty of a two-dimensional case. In higher dimension, we cannot expect such behavior. So which means, so this is an example of Cassini, Tanaka, Vidacek, 2018. So for any prime P and for any algebraically closed field of characteristic P, sorry, let me go to the next page. There exists a F. F is a polynomial of, F is an element of four-dimensional polynomial ring over K, X, Y, Z, W, such that hypersurface defined by F, and yeah, I take localization. This is KLT, but not F regular, or more strongly, not F pure. So you can choose arbitrary sufficiently large prime, but still, if you choose but equation, then you can get a hypersurface which is KLT but not F pure. So equation is something like this. Equation is F is equal to the GXY Z plus W to P. P is a characteristic, and this part is a homogeneous of degree 3. And more precisely, G is a defining equation of a super-singular elliptic curve. So then, yeah, you can get such example. So theorem is really a specialty of two-dimensional case. Yeah, anyway. So then, from now, let me talk about the geometric application. So from now on, my x is now my x is zero locus of C, zero locus defined like this. Fy a1 dot an is equal to 0, and I is from 1 to R. And Fy is a polynomial. Then, yeah, of course, X is a subset of Cn, and we can view this as a subset of Pn projective space. And we choose, so let's see the element of a projective space, like this, then we can consider hyperplane associated to C like this. So HC is defined to be a set of element of Pn such that CIAI, summation of CIAI is equal to 0. So this is hyperplane. Then we say that general hyperplane H satisfy some property P if, so this is the definition, if there exists a non-empty open subset, I mean Zariski open. This is a Zariski open subset such that for any C in U, associated hyperplane satisfies P. So this is just definition, but then in algebraic geometry, so the following is a natural question. So let H be a general hyperplane, and I assume H does not contain X, and if X satisfies property P, then does intersection X with H satisfy the same property P? Yeah, this kind of problem is very classical in algebraic geometry, and Miles Reed proved the following: if X has only KLT singularity, then intersection with H also has KLT singularity. Yeah, this is very classical result in birational geometry, but yeah. Oh, sorry, let me explain the key proposition, key to the proof of theorem. Key is a theorem, so-called second theorem of Bertini. This is so-called second theorem of Bertini. So here, so I use some algebraic geometry, so maybe some of you cannot understand the statement, but it's not so related to the other part of my talk. So just let me explain a little bit about the algebraic geometry. So assume X is smooth over C, and lambda is a linear system on X. So linear system is a vector space consisting of linearly equivalent divisor, but yeah, it's not important. Anyway, if this linear system is base point free, if linear system satisfies good condition, then general element of lambda is also smooth. If X is smooth, then so general element of base point free linear system is also smooth. That is a statement of Bertini. And using this, so using this, we can prove following. Let pi be a resolution of singularity, resolution of singularities. And H is a hyperplane, so H is a subset of X. And we consider product of H. This is a subset of X tilde. Then, if H is general, then by Bertini, we may assume product of H is also product of H is smooth. So which means pi inverse H to H. This is the restriction of pi. This is the restriction of pi. This become a resolution of singularity. Is a resolution of singularity of H. So pi is a resolution of singularity of X. But if H is a general hyperplane, then because of Bertini, so the morphism from pi inverse H to H is also a resolution of singularity of H. Is a resolution of singularity of H. That is a point. That is a key point of the proof of Miles-Reed. And my question is, what if characteristic P the problem is second theorem of Bertini this theorem fails in positive characteristic. So we cannot use the same argument as the argument of Miles-Reed. We need a different idea. And but in a joint work with Sato, I proved the following. If X is a three-dimensional quasi-projective, affine is fine, quasi-projective variety over algebraic closed field of characteristic P, and again H is a general hyperplane. If characteristic greater than 5 and X has KLT singularity, then intersection with H also has KLT singularity. Yeah, compared with the result of Miles Reed, I need this assumption: characteristics is greater than 5. But if you assume this condition, then we can prove similar statement in positive characteristic, at least in dimension 3. In dimension 4 or 5, then we don't have a resolution of singularity. Then problem is, yeah, I don't know how to attack this problem. Okay. And in order to prove theorem 4, I use theorem 3. So in order to prove theorem 4, I use a theorem 3. Theorem 3 is which one? This one. Theorem 3 is this. So in dimension 2, characteristic is greater than 5, then KLT condition implies F-regularity. I use this theorem. Yeah, let me explain how to use this theorem 3 to prove theorem 4. Yes, our x, yeah, let me assume x is affine. So like this, so as before, x is like this. And so x is a zero locus of the Fi. And Fi is a polynomial. Then, yeah, of course, x correspond to the ring, quotient ring of polynomial ring over F1 dot Fr. And let me denote this ring by R. Then, so x has KLT singularity means R is KLT. Yeah, precisely speaking, every localization of R is KLT. Then, maybe let me write here. But then KLT condition is preserved under localization. So RP is KLT for any P of spec R and with dimension RP is equal to 2. Yeah. So what I mean is codimension 2 point. So for every codimension 2 point, RP is KLT. Yeah. Of course, R is KLT, then the localization of R is also KLT. But then RP is two-dimensional. Here, and since we are assuming characteristic greater than 5, we can use theorem 3. RP is now F-regular for any P with a dimension RP is equal to 2. Here, we use the fact F-regular locus is open. F-regular locus is open. So RP is F-regular for every two codimension 2 point, and R is a three-dimensional ring, and F-regular locus is open, which means RP is F-regular for all P except for finitely many maximal ideal. Except for finitely many closed point. But we are interested in the singularity of the intersection X with H. The H is general, so we can avoid a finitely many cross point if we choose H suitably, then we can avoid finitely many cross point. So which means we may assume sorry, X is F regular. So R correspond X correspond to R, and RP is F regular, except for finitely many cross point. But yeah, but as I explained, so we can avoid finitely many cross points. So then we may assume X is F regular. Here we use the result of Carl Schmidt and Wenlian Tan. Schmidt and Tan, 2013. Again, X is a quasi-projective variety, and I assume X has a F regular singularity, and sorry, everything is defined over algebraical closed field of characteristic P. And as above, H is a general hyperplane. Then, in that case, intersection with H also has F regular singularity. So, which means so basically Bernoulli theorem holds for F regular singularity. So using this, so we may assume X is F regular, but so by the result of Schmidt and Wenlian Tan, then intersection with H has F regular singularity. Then by the result of Hara and Watanabe, so their result claims F regular always implies KLT. So then intersection with H has KLT singularity. So that is a proof. And yeah, let me emphasize so I used theorem 3 here. I use theorem 3 here, but the point is since we consider localization with respect to codimension 2 prime, the residue field of RP, I mean this RP, is not algebraically closed, or even not perfect. So so that's why Hara's result is not enough for this application. I need to, sorry, let me go back to theorem 3. Theorem 3, and if residue field is algebraically closed, it was proved by Hara more than 20 years ago, but Sato and I generalized Hara's result to the case where residue field is not necessarily algebraically closed, just a finite field. So this is because of this application. Oh yeah, sorry. Too much. Yeah, Bernoulli theorem is a very classical result in algebraic geometry, but as I said, so it fails in positive characteristic. So in positive characteristic, so I mean algebraic geometry in positive characteristic. I mean, study over non-perfect field is very important, and we can apply commutative algebra to that setting. So I think, okay. So then I talked almost everything I wanted to talk about today. Maybe, but sorry, actually, but I have one question. So let me give one question, which I don't know the answer. Yeah, question is the following. So, yeah, question is about F-regular singularity, but okay, anyway. My question is, maybe it's due to Hoekstra. I don't know the detail, but okay. Let be F-regular. Yes, precisely speaking, strongly F-regular and Henzelian local ring such that residue field is algebraically closed. Yeah, I don't know. So I don't know whether we need a Henzelian assumption or an algebraically closed field assumption, but yeah, at the moment, so let me assume this. Then question is, divisor class group is finitely generated? Yeah, because the answer to this question is yes, if dimension of R is less than or equal to 3. Dimension 2 case is classical. This is due to Lippmann. Basically, F-regular local two-dimensional F-regular ring is rational singularity, and divisor class of group of rational singularity is intensively studied by Lippmann. And dimension 3 case, so this is a recent result due to Karl Bahar. Yeah, sorry, I don't know precise pronunciation, but Karl Bahar Rojas and Alexis Stabler. This is 2020. Yeah, I'm not sure. Oh, sorry. So at least in dimensions, at most dimension 3, so it is yes, and this is one evidence. And another evidence is the classical result of story. If local ring is analytic C algebra. Yeah, sorry. Let R be an analytic C algebra. Yes. And then if R is a rational singularity, then divisor class group is finitely generated. But his proof uses exponential sequence, so which we cannot use in positive characteristic, and maybe so this question. So yeah, in this question, I assume ring is F regular, but maybe F rationality is enough. Yeah, just I don't know. Anyway, so F regular or F rational, so I don't know the answer. So that is my question. So if you know anything about this conjecture, this question, so yeah, please let me know. I'm very interested in this question. Okay. Okay. Thank you very much. Let me stop here.
Thank you very much, Shunsuke. We will take questions. Can open your microphone and ask questions. I have a question in theorem 2.
Theorem 2, sorry.
Yeah.
Theorem 2 is...
Theorem 2, that was the characterization of log canonical singularities in terms of Q Gorenstein and F pure.
Yeah.
And the part 3 said that if there exists a closed point, so that R mu is Q Gorenstein and F pure. That is equivalent to R being log canonical. So my question is, can you replace log canonical by rational singularity and F pure by F rational in part 3?
Yes.
I thought only 1 and 2 were proved earlier. Part 3 is also true for rational singularity and F rational.
Yes, that is true. Yes, that is, I mean, okay, maybe let me write here. So that is the main result of, sorry, it's a, this is a theorem Marshwood. And for rational singularity, we don't need Q-Gorenstein assumption, just the following are equivalent. And first one is R is rational singularity. And second condition is, I mean, there exists mu. This is non-empty open. And R mu is F rational for any mu in U. Mu is a closed point. And the third condition is there exists one mu in spec A. So this is a closed point such that R mu is F rational. So about F rationality, so everything is fine. But KLT, I mean, F regular case and local F regular case and FPR case, especially FPR case. So we still have some conjecture. It's not proved.
So I have one more question. Dale Katkowski, in I think 1990, characterized rational singularities in terms of product of complete ideals being complete or square of a complete ideal being complete. So since there is a good correspondence between rational singularities and F-rational rings, can one say that in an F-rational ring, product of tightly closed ideal is tightly closed?
Maybe not, but maybe so such question. So you should ask KH. Yeah, KH is an expert, I think.
So he proved that powers of parameter ideals are tightly closed in a F-rational ring. But is it true that product of any two complete tightly closed ideals is tightly closed? That will give a perfect correspondence between the result of Katkowski and what is going on in F-rational rings. I don't think we know a characterization of rings which satisfy the property that product of all tightly closed ideals is tightly closed.
Yeah.
I have seen a characterization of such a result.
Yeah, to be honest, I have never thought about such kind of question, but how about Keiichi?
Actually, you have proved that perhaps only in dimension 2, but in that dimension 2, products of any parameter ideal is tightly closed in F-rational ring.
Yeah, in any dimension. In any dimension,
in any dimension.
Yeah, I'm asking in any dimension.
But Katkowski's result holds only in dimension 2, and
yeah, Katkowski result is in dimension 2. So one has to first begin, because dimension 1 is trivial. Dimension 1 is sort of trivial. But the non-trivial, I think the open case is dimension 2. Whether at least suppose product of tightly closed ideal tightly closed, will it imply that the ring is F-rational?
Good question, maybe. Of course, I don't know the answer.
I mean, of course, this dictionary, the dictionary between birational geometry and characteristic P singularities, seems to be growing by the day. So what I do, I take a theorem about rational singularities and I ask the same question for tight closure. So I don't know what is not true. Is there a property of rational singularity in dimension 2 which is not true for F-rational rings?
Yeah, good question.
Anyway, yeah. So are there any questions? Any other questions? Anyway, one philosophical question is why this is happening. I mean, these singularities were they were discovered by completely different motivations. F regular rings didn't exist before 1990 or 1987, but the KLT singularity is quite old, I suppose, or log canonical.
Yeah, it was introduced late 70 or beginning of 80 or something. Yeah.
Right. So it seems like an accident, or is there a deeper philosophy working here?
Yeah, but for example, I don't know who observed such correspondence first. So maybe Keiichi, or I don't know, Hoxton or Huneke. Yeah.
No, but in work of Hoxton Huneke, I don't find mention of singularities in characteristics 0.
But, yeah, but maybe for me the starting point is Feder's paper. So
okay,
Feder discussed relationship between F purity and rational singularity, and I think that paper gives us some hint to geometers, I guess.
Right. Yeah. And then later on, the test ideals suddenly acquired correspondence with the multiplier ideal, and that is also a surprising connection.
Yeah.
So the dictionary is becoming bigger and bigger, so there must be some explanation about why this is happening.
Yeah. So one explanation is how should I say it? mean, Carl Schwitt gave a common definition of multiplier ideal and test ideal. So which means his definition gives multiplier ideal in characteristic 0, and his definition gives test ideal in positive characteristic. Same definition gives, I mean, so yeah, such kind of phenomenon was observed, but philosophical reason is quite difficult to explain.
Yeah.
So sorry, yeah, I don't know good answer, so just.
Okay. All right, Shunsuke, very interesting talk. Thank you for giving 2 talks so that student audience can understand, and you pointed out many interesting questions. So thank you very much for coming to this seminar.
Yeah.
Thank you.
Thank you very much.
We'll end the meeting now.